Hello students, from the Department of College 8 and Technical Education in the Learning Management System. We were discussing about the analog modulation and demodulation concept. Let's start with today's session. In the previous session, we discussed about the basic concepts of electronic communication, block diagram of electronic communication, and different types of electronic communication. In the session 2, we discussed the differences between analog and digital communication, as well the difference between the baseband and broadband communication. In the third session, we discussed about the modulation and need for the modulation. In today's session, we are going to discuss about what is amplitude modulation, and we are going to discuss about the transmitter of amplitude modulation and how we can represent the amplitude modulation, the mathematical expression for amplitude modulation. Let's begin with the session. Amplitude modulation. In the previous session, we discussed the modulation means here it is varying the characteristics of carrier. Means the carrier is a high frequency signal, as we explained in the previous class. It will be having certain amplitude, frequency, and phase. So these are all becomes a characteristics. If you are varying the characteristics of this high frequency carrier in accordance with the message signal, baseband signal is also called as a message signal or a modulating signal. So this is called modulation. If you're varying the amplitude of the carrier in accordance with the message signal, then we can call it as amplitude modulation. So here we have a definition for the amplitude modulation. The amplitude of the carrier signal is varied in accordance with the instantaneous amplitude of modulating signal. So here you can observe the waveform of the amplitude modulation. Here you can observe the high frequency carrier whose amplitude are going to vary in accordance with the instantaneous value of the message signal. Here the envelope of this message signal, whatever you are observing here in the amplitude modulation output, this is having all the instantaneous values of a message signal or a modulating signal or baseband signal. So this is a wave representation for amplitude modulation. Let's discuss the block diagram of AM transmitter. Here we AM transmitter means here at the transmitter side we need to do the modulation process. For the modulation process, obviously there will be a low frequency signal that we are taken it as an audio signal. So this audio signal we are strengthened by using a preamplifier. This amplified modulating signal we are giving as an input to a AM modulator. The another input for this AM modulator is the high frequency carrier that we are taking it from the RF oscillator. These are all the two frequencies we are giving it for an AM modulator. Here, audio frequency is a low frequency signal and radio frequency is the high carrier signal. So after modulation, the signal is going to be modulated. This signal is called modulated output. This is power amplified and then we are passing that through the antenna. This is how the AM transmitter works. So we can observe here, this is a audio signal at the one end. At the other end, we are taken on radio frequency from the oscillator that we are superimposing. That is a modulation we are doing. At the output, we are getting a AM signal. Here, these are all the waveforms that represents the information signal with a certain amplitude and the frequency, and the carrier signal with a certain amplitude and the frequency, Here the amplitude we can consider as a VC, and for the message signal we can consider as a VM. And similarly, the frequency of the message signal we can consider as a FM, and like here we can consider the amplitude of the message signal as Vn and the frequency of the message signal as Fn. The amplitude of the carrier here we can consider as a small bc, and the frequency we are going to consider as fc. And the overall this maximum amplitude of the signal we can take it as a. So like this, we can get a modulation. Yes. Now how it works? Audio signal, whatever we are having, there's always a low frequency signal that we are going to amplify. That signal we may get from the microphone. So microphone is a transducer which converts the audio voice signal into an electrical signal that is going to be pre-amplified for the purpose of boosting the level of that modulating signal. That and radio frequency signal which generates the high frequency carrier. Both this modulating and carrier signal is sent to the AM modulator. Then the power amplifier is that is used for amplifying this modulated AM wave, which can finally we can pass through the antenna. This is how the AM transmitter works. Next, well, we are going to discuss about the mathematical expression of AM modulation. How we are going to get a amplitude modulation. Here, the mathematically we can express the carrier wave. This is a C of t. Here we are going to consider the instantaneous values of sinusoidal carrier wave. So as we observed here, the carrier is a high frequency signal and which is having certain amplitude and the frequency. And similarly, the message signal, here this we are taking it as the instantaneous value of the carrier as C of t, that is a carrier with respect to the different timing, and the message signal is like we are taking it as M of t. The M of t we can represent the instantaneous values of message signal. Here, the C of t is the instantaneous value of the sinusoidal carrier. We can represent it as Vc sine omega t because we are considering the sine wave, where omega c is the angular frequency of the carrier. So omega c we can represent as omega c is angular frequency, so that we can represent in terms of 2 pi fc. We know the fc is carrier frequency. Similarly, the omega m, this omega m we can represent as 2 pi fm. We can represent as 2 pi fm, where fm is message frequency. So here these are the instantaneous values we are going to represent. And we modulation index is another term, which in that the how much the percentage of modulation we can determine using this parameter. There is a modulation index. The modulation index that we can define as a ratio of the modulating voltage, amplitude of the modulating voltage, or a message signal to the amplitude of the carrier wave. So using these basic terms, we can determine the amplitude modulation envelope of the voltage of the AM signal. How actually we can determine the AM means this is actually our AM signal. So AM signal, we know amplitude modulation signal Here, this is the carrier amplitude. The carrier amplitude is remains same because the amplitude of the carrier wave is going to vary in accordance with that of the message signal. We can observe here, this is a message signal that is formed as an envelope of this AM signal and the either side of the carrier amplitude in the both positive side as well as the negative sides. You can observe here, this is a message signal. So the amplitude of these, whatever the red color lines are going on here, these are all the carrier waves that is going to change. The carrier wave, the amplitude of the carrier is varying in accordance to the message signal. Here, this is the amplitude is VC, and this amplitude here it is VM. So this amplitude, the V minimum, and this is the V maximum. So the V minimum is the minimum variation. Here we can observe the minimum voltage. This is V minimum and this V maximum. The amplitude where we are having a maximum carrier voltage and here we having a minimum carrier voltage. So from this diagram, so here we can observe here, this is the unmodulated carrier and this is the modulated carrier because this carrier amplitude are varying. This is having a minimum amplitude and this is having a maximum amplitude. Okay. The amplitude of this AM signal, we can determine the amplitude of the VM signal. This is a maximum amplitude from this reference point. So A, that we have taken it as A, the A we can represent as VC plus its the amplitude is varying according to the instantaneous value of the message signal. That's why we have written here A is equal to VC plus VM sin omega t. ಇಲ್ಲಿ ನೋಡಿ, ಇಲ್ಲಿ VC that is the voltage of the carrier. ಇಲ್ಲಿ carrier wave ನೋಡ್ತಾ ಹೋಗಿ, ಇಲ್ಲಿ carrier wave ನಿಮಗೆ ವೇರಿ ಆಗ್ತಾ ಇದೆ. ಇದು ಮೆಸೇಜ್ ಸಿಗ್ನಲ್ ಪ್ರಕಾರ ಮೆಸೇಜ್ ಸಿಗ್ನಲ್ದು ಹೇಗೆ ಆಂಪ್ಲಿಟ್ಯೂಡ್ ರೈಸ್ ಆಗ್ತಾ ಇದೆ ಅದೇ ತರ ಹೇಗೆ ರೈಸ್ ಆಗ್ತಾ ಇದೆ ಕಡಿಮೆ ಆಗ್ತಾ ಇದೆ ಆ ತರ ನಿಮಗೆ ಕ್ಯಾರಿಯರ್ ವೇವ್ ಸಹ ನಿಮಗೆ ಕಡಿಮೆ ಆಗ್ತಾ ಇದೆ. ಸೊ ಹಾಗಾಗಿ here we can represent the A is equal to VC plus VM sin omega t. So we know VM, so according to the modulation index formula, so MA is given as, here it is VM divided by VC, VM divided by VC. So this is the formula we discussed. So we can represent that VM in terms of MA into VC. Here we are replacing this term with the MA into VC. So I'm going to take a VC common. It becomes 1 plus MA sin omega mt. Okay, so this will be the amplitude of my AM signal. Let's determine the instantaneous value of this AM signal, how this envelope is going to vary. So that we can determine using this formula, the small v is equal to, it is a small v is A sin omega ct, where VC is A is given as VC 1 plus MA sin omega mt into sin omega ct. So this is given as VC sin omega ct plus MA VC sin omega ct sin omega mt. So we can represent this. We are separating these terms, VC sin omega ct plus MA omega c. Here we have the sin omega ct and sin omega mt. This is in the form of sin A and sin B. According to the sin A and sin B, we have formula. This is actually the minus half of cos omega, cos A plus cos B minus cos A minus cos B. So according to the formula here, sin A plus sin, okay, sin A into sin B, sorry, sin A into sin B is given by the formula as a minus half cos of A plus B minus cos of A minus B. So if we write, we are substituting here the A and B, we are taking it as omega ct and omega mt. So similar way, if we write this, so this is the formula. Here we are written that the cos, this is half only we are taken here. So if we multiply with the half, this minus term will come first, then minus cos A plus B. So similar way we are written here omega ct minus omega mt minus cos omega ct plus omega mt. So the multiplying this whole term, this is MAC divided by 2 with this values internal, the flower brace, inside the flower brace, we can split like this. The V, the amplitude of the envelope instantaneous value of the AM signal, we can write it as VC sine omega CT plus MA VC by 2 cos omega CT minus omega MT minus MA VC by 2 cos omega C plus omega M into T. So we have this finally the equation, the mathematical representation of an AM signal we can represent like this. So here we have the three terms. This is the unmodulated carrier signal. This is like a C of T. This is an equation as we discussed in the previous slide. This is same as a C of T, that is the instantaneous value of the carrier. That's why we can say it is an unmodulated carrier. Here, this is the lower sideband where omega ct minus omega c minus omega m, this will be a lower band of frequency which will come. The omega c plus omega m, this is the upper band. So we can call it as a lower sideband and it is the upper sideband whose amplitude is MA VC by 2, here same amplitude. So we can represent this mathematical representation of a AM in terms of a sidebands. Here, if you plot the frequency versus amplitude, we can plot this AM wave as which is having an unmodulated carrier. You can see the long line. This is a FC. It is there at the frequency of carrier, is the high frequency, and below the high carrier frequency, the frequency you will get is a FC minus FM, where FM is the modulating frequency that will be that is, we can call it as a lower sideband, who's having an amplitude as MAVC by 2. Here upper sideband, which is at the frequency of FC plus FM, which is also having the same amplitude of MAVC by 2. So we can determine the bandwidth of this AM signal by taking upper sideband minus lower sideband. Here the upper sideband is at FC plus FM minus lower sideband is at FC minus FM. If here in this terms, this FC get cancelled out and we have the 2 times of FM. So the AM signal, it will be having a bandwidth of 2 times of FM. So now we'll discuss the modulation index in terms of Vmax and Vmin. In the mathematical waveform, we observed here the Vmax is the maximum amplitude of the amplitude modulated wave, and a Vmin is a minimum amplitude of modulated wave. Here, according to this diagram, according to this waveform variation, we can take Vm. Here this is a Vm, this is also the Vm. It becomes the peak to peak, it becomes 2 Vm. The 2 Vm, we can take it as is a Vmax minus Vmin. So here we have written here, if you take like here, 2 Vm is equal to Vmax minus Vmin. So I can write the Vm is equal to Vmax minus Vmin by 2. Similarly, the peak value of the carrier signal, you can represent the peak value. Here, this is a Vmax. This is from the reference to Vmax. So this is completely, this is V maximum. So V maximum is a 2 times of, this is actually the 2 times of Vc. So Vmax plus Vmin divided by 2. This is the maximum is 2 times of Vm. This is V maximum plus V minimum by 2. Fine. Next. If we know the MA, the modulation index is Vm by Vc. Here, substituting the value of Vm, this value V maximum minus V min by 2, Vc, V maximum plus V minimum by 2, the 2 get cancelled. If you here the MA is V max minus V min divided by V max plus V min. So this modulation index we can determine by using the formula V max minus V min divided by V max plus V min. Let's discuss one problem on this. Suppose an AM signal which is having a V maximum of 15 volts and V minimum of 5 volts. Then determine the modulation index and calculate Vm and Vc. This is the question. So first, we need to determine the modulation index. As we discussed in the previous slide, the MA is given by the formula Vmax minus Vmin divided by Vmax plus Vmin. So MA is given as 15 minus 5, 15 plus 5 is 0.5. So we can determine the Vm. Vm is given by the formula Vmax minus Vmin by 2. The Vmax is given as 5 volts and Vc as 15 plus 5 divided by 2, it is 10 volts. So in today's discussion, in this today's session, we discussed about the amplitude modulation, the amplitude transmitter section, and as well as a mathematical representation of a modulation, amplitude modulation. And we have a look on the modulation index. Let's discuss the multiple choice questions on this session. Question 1, an AM wave may be represented as E of t sine omega ct, where E of t is envelope of AM wave, B carrier signal, C amplitude of modulating signal, D none of the above. So answer is A, envelope of AM wave. Question number 2. In transmitter, dash oscillator is used. Options are Hartley oscillator, B RC phase shift oscillator, C Wien bridge oscillator, D crystal oscillator. The answer is D crystal oscillator. Question 3. In India, dash modulation used for radio transmission. Options are A frequency, B amplitude, C phase modulation, D none of the above. Option B, amplitude modulation. Question number 4. In AM wave, useful power is carried by dash. Carrier, B, sidebands, C, both the sidebands and carriers, D, none of the above. The answer is B, sidebands. So we observed in the AM wave, we have three bands. One is carrier and the two sidebands. The most of the power is carried in the sidebands that we are going to discuss in the next sessions. Fifth question. In amplitude modulation, the bandwidth is dash the audio signal frequency. Option A, thrice. Option B, 4 times. Option C, twice. Option D, none of the above. Answer is option C, twice. The bandwidth is twice the audio frequency signal that we discussed 2 times of FM. The question number 6. The amplitude modulation. The dash of carrier is varied in accordance to the strength of the signal. Options are amplitude, B, frequency, C, phase, D, none of the above. Answer is A, the amplitude of the carrier. Question number 7. The AM spectrum consisting of option A, carrier frequency, B, upper sideband frequency, C, lower sideband frequency, D, all of the above. Answer is D, all of the above. As we saw in the spectrum, we have three sidebands: carrier, upper sideband, and lower sideband. Question number 8. The radio frequency oscillator generates the carrier signal. This is right, or true, or false. Answer is true. Question number 9. A AM broadcast station transmits modulating frequency up to 6 kilohertz. That is FM. Modulating frequency means is the message signal frequency. If the AM station is transmitting on a frequency of 894 kilohertz, that is carrier wave, the value of maximum and minimum upper and lower sidebands, the total bandwidth occupied by the AM stations are option A, 900 kilohertz, 888 kilohertz, 12 kilohertz bandwidth, B, 894 kilohertz, 884 kilohertz, and 12 kilohertz bandwidth. C, 894 kilohertz, 888 kilohertz, and 6 kilohertz bandwidth. D, 900 kilohertz, 888 kilohertz, and 6 kilohertz bandwidth. We need to calculate here the maximum upper sideband and minimum, that is the lower sideband frequencies according to the spectrum. So answer is A, 900 kilohertz, that we can get, that is a maximum frequency, that is upper sideband, by adding the FC plus FM. The FC is 894 plus 6, that is 900 kilohertz, and the minimum frequency is a lower sideband frequency, that is given as 894 minus 4, the 888 kilohertz. The bandwidth is given as the difference between the upper sideband and lower sideband. So the 900 minus 888, so that will give you the 12 kilohertz. That is nothing but 2 times of 6 kilohertz. That is 12 kilohertz. The answer is A. So from this, actually, we got this expression. Answer. The carrier frequency, lower sideband frequency, and upper sideband frequency. The bandwidth is lower upper sideband minus lower sideband. The question number 10. The AM spectrum consists of carrier frequency, upper sideband frequency, C, lower sideband frequency, D, all of the above. Answer is D, all of the above. Thank you.